most important journals around the world. He belongs to the SNA Event 3. You see that Scopus Award, like a research with most citations. So, it gives us the possibility to start the presentation.
Okay, thank you. Thank you for coming. So, entonces, voy a decirles algunas cosas importantes para nosotros, porque estoy decidida aquí. Tal vez es un poquito más difícil sorprender a ustedes con algo nuevo. Y por eso decidí, como un hombre didáctico también, darnos una plática general. Así me va a alcanzar el tiempo. Entonces, yo voy a dar la otra parte de plática que va a decir sobre líneas de investigación que estamos manejando en el laboratorio del Nobel de Santos de la UNAM. Entonces, quiero empezar mi presentación con ese video que muestra uno de los problemas principales, quiero hablar sobre dos problemas principales que aparecen en la teoría moderna del control y cuyas estamos tratando de resolver. Ese video muestra por qué. Porque aquí usted ve perfectamente un sistema híbrido que está switchando de manera periódica en este caso. Y además un sistema incierto porque si, por ejemplo, estamos preparando un labor para la Tierra, el piso no es asegurado, además puede ser mucho lodo, puede ser cualquier cosa. Entonces, de aquí vienen dos problemas principales de control. Uno, que ya tenemos que hacer el control sobre el sistema incierto. Porque si conocemos todo, no es cierto. Usted sabe que mi dicho favorito a veces estoy bromeando, no es un poquito trágico, pero es verdad. Y 27 años con mi primera esposa pensé que lo conozco porque la conozco bien. Pero estuvo alguna incertidumbre que se trató del matrimonio. And I saw that I know, but uncertainties appear. Yes. And the second question is that sometimes the processes in the life switch. If you are not sure that your control is able, in the moment near to the switch, have precise information and control precise the behavior of the system. After 100 steps, you will find. So, what we need? We need 2 points. 1, to be ready to uncertainty. 2, to converge and finite and better fixed time. So, why I'm doing this presentation? To promote religion. Because a classical religion you was going to the church. And then the priest told her, okay guys, if you will doing well, so after when you will die, you'll go to paradise. But if you will have some kinds of bad performance, I'm not sure. So that's precisely meaning how to life transform the ideal human. So what's happening in reality? In reality, you would like to be paradise when you life. Not over. We would, as you can see, sometimes we wouldn't like to follow the diet. That's the point. So we need to be prepared to robustness, and we need to be robust, and we need to act quickly in order to have a final end or fix the problem. So that is why I will present you I will start with simplest example, showing this table, and I will use generally two examples. One is this table, so what happens in this table? This table is stable by gravitation. So I'm putting perturbation, nothing happens. And another example is, you see, two-fold, how people are making the world of life. They are putting two policies. The policemen are bringing you in the correct way. And if you try to go away, you will have a push. So, why is it important? Because it's the best example of the situation I would like to explain why. You see, first of all, the policy for sure will bring you in the correct way, but if they will beat you in each step, what will happen? Or they will say, guys, you are paying me too small for such a strong war. So, or they will kill the prisoner. So, what does it mean from the viewpoint control? So you should take care of the theaters or of the plan. Otherwise, you will blame the plan or you will destroy the theaters. So let us see an example. Consider this is mechanical system and this is equation of velocity, not about position. If it is so, you will see that this term is a drive friction term. So you will see if I'm putting the perturbation, the policy will bring me to zero. What does it mean? It means that if you are making the brake, your car will stop. Pay attention. If you put the model of this constellation, your car will never stop because it will converge asymptotically exactly to zero. So, and then you are trying to follow zero, and you will follow because you will stop. If you will see this same example from the viewpoint of policy, so all the policies, they will bring you to the correct rate, and they are starting to beat you in each step. So, what's more important here? There is one other idea behind. You see, if I just start with this table, what's happening? That's boring. So, what's happening? You'll see that even I know the friction. I know the friction. That's the third both new. So what's happening here in this situation? If I will filter out these beautiful policies, what I will get? Oh God, I will have the same information I put it here. So it's very simple example of the control law I would like to propose. I would like to propose a really control law. And it is very clear and very strange that when I will try to filter out, I have that sine function is equal to sinus function. That's also funny, isn't it? So what does it mean? This means that if I have even a number of speeches, no one classical control theory differential equation theory will work, because we don't have even classical existence theory for such class of system. That's the point. So that is why there are two important rules. One, from the viewpoint of mass mathematicians, was needed a special theory for such a kind of equation. Number two, consider that from the viewpoint of mechanical system. As such, dry friction you control the position, the velocity, but you know the position. What does it mean? This means that you will for sure stop, but you don't know where, before step or after step. I think it's also a very important stuff. So, with such kind of equation, people have understood that they will certainly stop, but they don't know where. So, from engineering viewpoint, it was not a good control because they didn't have the control over position. From the other viewpoint, they cannot manipulate both x1 and x2 in the same time. And from mathematical viewpoint, the definition of solution, if you become discontinuity surface, was needed. And from the engineering viewpoint, it was also clear when they started to simulate. They have a chattering. Chattering means speak very fast. So here I will show you the video in which you can see a real chattering in the system. So, and that's really the point to start. So the hard investigation at that point was started in different fields, and it was started from both fields. One, it was a very strong group of mathematicians governed by the dragon, and they've discussed now dragon what's happened with such kind of equation. It is also very important to mention that one Mexican professor, which just died, Professor Zeiger, he done at that time his PhD thesis in Germany. And he was working also in the range of mass devoted to discontinuous, to the equation with discontinuous values. And it was my pleasure to know him for that. And he was Yuan professor, Professor Yuan in yes. So, but generally, the general concept was done by Professor Friedman. So, first he published in 60s, and what he does, he left equation with discontinuous values. We cannot consider it like equation. And it was a shock for the people. Why? You can see, this is precisely the case when we have this continuity. It is dry friction. So, the positions in the velocity of the table will be the same for a big class of different perturbations. So, for a different class of perturbations. That's the point. So, you cannot consider only equation. You can consider inclusion. When I started with, I started with diet. So, the diet should be known, could be known so strict, and you can follow the same rule, the same rules, the same. So, that's very important. What he told, okay, what we need? We need to consider differential inclusion. And this differential inclusion should be formed for all complex minimal common exposure of radical side without the sets of measure zero. So, can you imagine that some engineer of 60s can use such a definition in his work? So, then people makes one step more. He tried to explain how it works in reality. So, he told, okay, you need to slide. What does it mean that you need to slide? This means that you need to smooth, like this one. So, slide this means to be every time in tangential surface. If you are cutting, you are not sliding here. Yes, it's true. So, what he told? Okay, you need to make a convex closure. This means you need to connect the ends of the vectors by effective F9 and F1 as the sample set. And then you can find the vector or the vectors which are in intersection of the set with the tangential surface. Okay, this means slide. Also does then, engineer's key. You can see here my scientific father, Professor Ruti. It is 64 photo. And yes, now it's a little bit more older. Like 70 years old. 50 years old, yes. And this is my scientific father, which is also still alive, and some of you maybe have seen him in 2011 in Milan IFA Congress. So, what's it talking? Very simple stuff. They told, okay, guys, all of the field of development was not considered. It was a different equation. When we are playing on the field of differential equation, we cannot understand what's happening with the system if we are playing with control. But if we are playing with the control system, we have hands-free system in the sense that control is in our hand or in the hand of the workforce. If you would like to slide, what's really happening? You see, there was a great thing. We need to slide to the surface. So this means that you have to be in tangential surface. So what does it mean? This means that you need to have the derivative of surface as 0. And G here is a simple gradient vector of the surface. So, what is it? It is if the system is are fine. This means that you have a simple system of algebraic equation. So even engineers can solve it. Even engineers can find equivalent control. What does it mean equivalent to? It is the control which ensuring you to slide. So finally, what you need to solve such equation and substitute it in the universal system. You will tell me that it is not so clear because you've told me it's about equation of sliding, and this is an equation of the same dimension as the initial one. So what you need to do, you need to see if you are really sliding here. So what you are doing, you are putting gradient here, gx dot is g is equal to gf, gb for gb minus 1 will be eventually, you will have gf minus gf 0. It's done. So we are sliding, but we have a whole dimensional equation. That's the point. So, okay, but it was not endlessly. Why? Because mathematicians, what they are doing, a god or people are giving them the system and they are analyzing them. The control people are very different. Why? Because they are active. They can change the system. They have to change the system in order to have desired properties. So mathematicians didn't have the right to change the surface. The system is discontinuous. So what they done? They told, okay guys, we are active people. We can also move discontinuity surface in order to have it the desired property of the system. Okay, let us do for mechanical system the simple lining surface. What we'll have? We will have C in our hand as the active people. So what we'll have? You see, the position will be go to 0, not in finite time, but so fast as we want. C is in our hand. If you want that it will be vanish fast, we can make C determine pictures. That's all. That's what we have to do. And the same is with velocity. So they introduced a sliding surface which is different from gravitational surface. So in that way, what we can do, we can slide around the surface and we can go to 0 in infinite time. So it is part of religion I was promised you to promote. Why? Because it is these motions are not depending from perturbation. Why? Because the policy, the sliding mode control, will move you near to the surface or into the surface. But you will not depend not on control, nor on perturbation. So that's the first part of religion. Why the first? Because you will be happy when you will die. Yes, when you will die. Because you will have infinite time. So, that was the first principal step of the theory. It was done in the 60s. And as usual in human relation, as usual in the world. So, when you are still in love, you have overshot. When you introduce the new method, the new medicine, you practically sure that it will help you for all disease. It's not true. So then the next step was written. So Professor Rajevic made your PhD thesis, and he showed that, okay, you can ensure in some cases that your motions are invariant with respect to perturbation. So you cannot follow the diet directly, but still there is a restriction. Why? What the restrictions are? Your perturbation should be in the space generated by the matrix of control. So, in some sense, your perturbation should be reachable for control. If they are not reachable, you have unmatched perturbation. So, generally, the result was that the clavicle system are invariant with respect to perturbation if and only if the system could be written in this form. You see, here is lambda are perturbations, and they are inside of the span of matrix. This means that you can reach such perturbation with the help of control. Otherwise, it doesn't work. And then it was a thesis by Professor Lukyanov. Professor Lukyanov regularized the procedure how to rig a clavicle. He made it in 2 steps. Step number 1 is to transform the system into regular form. This means you have to play like you are playing video. So you have one ball, another ball, so you can just put one first ball through the second. So what does it mean? You transform the system into system 1 is the system describing the motion in matched derivative in the space generated by control matrix. And another one is the system which theoretically could be invariant if the perturbation were matched. So all perturbation will live here, and this part will be invariant with respect to control. So what Professor Lukyanov told? To design for such a system, clavicle control is very simple. So first, you need to go to the church you are trusting in, and you would like, and you will have a fictitious control which will stabilize or optimize or whatever the system. But this system is ideal, easy invariant with respect to control, and it is invariant with respect to control. So any church will give you a desired behavior. Then you are going to policy and tell them, okay, please follow the rules of the church. That's how society is working. So, and clavicle control policy will bring you into this surface, and you will follow it, and you will have for sure the behavior approved by the church, and you will reach the goals you need, but that's the point. So, finally, what we've reached till the age of 80. Till the age of 80s, we thought, okay, clavicle control is precisely the sense that he can compensate the perturbation in that matched space. Point number one, we have time finite conversion, but to the surface, but not to all of variables we would like to deal with. And it was also working only for bounded uncertainty. So, what were the disadvantages? Disadvantages, principal disadvantage was the chopping effect. Then, of course, we need to have a system with relative degree 1. What does it mean? We need to find all of the derivatives of one and put it inside of the surface. That's it. Then, sliding variables converge when we will die. So this means asymptotic. And they was insensitive only against of matched equations. So that was a result of the first generation of sliding control. Then you start with work. So here we are with Professor Lam. We started to work in early 80s on our PhD thesis. And then after 10 years, the group of Professor Bartolini was joined us, and you see Professor Bartolini, Professor Ferrara, Professor Pisano, Dr. and Professor Rosaini before there was like his notion. So finally, what we have, remember, we was working with the mechanical system, and we have finally said what? We have a possibility to reach zero in error in 5 position and velocity through the surface, and the surface guarantees us that we will go for sure to zero, but then we will die. So, what we have? We invented the algorithm called twisted algorithm. What's the idea? The idea is the following. First, to move this table, we need to apply the force more than gravity. If we will not do it, so we will not move. So we need to apply dry friction more than we need to apply the control here more than dry friction. So B should be for sure greater than alpha. That's for sure. Then what will happen? I'll go to the desired position. I cannot stop immediately. I can change only the sign of acceleration, but not the velocity. That's what happened. So that is why we need to change. We need to see what's happened, because we will go through zero position, and then after that, what will happen? This sign will also change. So we will have a sign of acceleration, and then we will change the velocity and we will return back. What's in reality happened is the following. You see here the behavior of the plan, and in fast plane, and you see we will have infinite number of switches. What's the difference here is between a linear system and this one. If you are doing spiral in linear system, you have the same angular velocity. If you do this with a twisting, you will have accelerations in the sense that the time interval between the switches will form geometrically vanish geometrically sequence. And it will converge to the finite number. This phenomenon called Zeno phenomenon Then the phenomenon means that Zenon told that very strong Achilles will never reach a target. Because when the target will make first step, Achilles will reach you, but she'll make another small step forward. So when he will reach the next position, Turtle will make more movement forward. So, and this sequence could be quick, but also knows that Achilles will reach the target. So what does it mean? This means that this sequence will be challenging, but it will be converged to the system because it's vanished. So the same will be here. So what's finally that we can reach zero without going to the charge. What does it mean? That for mechanical system with this control, we can have finite integral. And also we could be invariant with respect to calculation. Moreover, if you will see the precision will be much less. I will explain you the idea of chattering. Why chattering happens? Because when you are switching fast, you have very small error in position, but you have big changes in velocity. So you need to split all of the energy of your system, like you are splitting juice from lemon. So what was our idea? Our idea was very simple. But if we need to put ideas of chatting, we need to make S and S total small simultaneously. If we cannot do it, we will lose the war with chatting. So, and it was a first step. The problem of this step was the following. To reach this goal, it was necessary to lose the velocity. And what does it mean? If you'd like to use such a controller for dealing relatively with one system, and we know the velocity, we know perturbation. So, if you know perturbation, you don't need to do nothing. Why you need sliding or control if you don't know perturbation? It's not the case. So, that implies the next step. We should do the same, but without derivative. And super twisting algorithm was created. This algorithm is much more different from the first one. Why? Because it is a continuous algorithm. Why it's continuous? Let's see. Here you have parabolic function. Because what I'm changing, for example, if x is positive, I have this part of parabola. If x is negative, I'm changing the sign here. So I have this part of parabola. But it's still parabola, it is continuous. The only point is that you have infinite gain to zero. Why? Because when you are differentiating, you will have 1 by square root in the denominator. It's new. This part is continuous. Why it's continuous? Because it is not only sine, it's integral from sine. And integral from sine is continuous. So we will have two properties. One, that we have second order sliding. So we will have future, but we will not use derivative. without checking what you see. Let us see maybe a movie to explain what's going to happen. So, you see, here is an experiment to control inverted pendulum. You see, I've put the head here, so maybe I'll put also. So, you can see, I have to put here a hand, and moreover, of course it's stable, the motion. But, if I will leave the motor working, in 5 minutes, it will be destroyed because of the high frequency needed by engines. You see, but you see the head is like a soldier in the red square. It's really robust. The problem is so unfortunately I cannot put the value because you can see, I saw that you will hear the chattering, but no. So now you can see the other experiment is super realistic. Nothing happened. No chattering. We've left the pendulum working for 1 night and nothing happened. So, if substituted, you will see, I'll show you 2 long videos to see how big it is. But it will be in the yes, of course. Yes, but I need to say the truth here is the following. Is continuous. Can we expect from continuous algorithm that can completely compensate this continuous perturbation? No. So, this algorithm has a property of sliding mode, but for the Lipschitz perturbations. Lipschitz in fact, they could be not Lipschitz in X, but they should be Lipschitz. That's very important. So, here is precisely 2 types of simulation of the same system. One is the first order sliding mode, another is the second. You see, from the same surface, the same finite time converter to the surface, the same behavior of the state. But you can pay to policy and they will not vary with you.
Well, you can see the first set of models in description of the business.
Why? Because you are reaching some image of S in the story. So it is a level of reduction of the space. Because if you are fixing 2 surfaces instead of 1, 2 surfaces instead of 1, so there's a reduction. So, moreover, you see, after that, it follows the rule. You see, here it is an example of simplest first order derivative. how people, so one of the main problems of control theory, you have to put derivatives. Even you would like to put PD or PID, you need to put derivatives. Otherwise, it will not work. And of course, for noisy signals, it is very important to have the differentiators with good properties. The logical model of differentiator is very simple. You can put the empirical system with a such discontinuity surface, x1 minus f, and x1 is additional variable. So it is clear that if the derivative from f is less than 1, so for sure you will have a sliding of this surface. If you will slide on this surface, you will tell that f dot will equal to sine of x1 minus f. Sine of x1 minus f. But as I've shown in the first slide, it was not clear why sine is equal to something. Remember my example of the first law. So you need to filter out this sine function in order to reconstruct the unit. And that was a crazy task because anyway you need filtration. You need to know it. Now let's go to supercritical and do the same. You will have signal without need of filtration. And you will have continuous signal. That's the main point people started to use differentiator based on supercritical. And it was shown that this differentiator can provide maximum possible precision, which is realizable for given sampling step and for given noise. It was famous theory by Collingworth when he showed that in the term of noise, for example, you can realize just 2 square root of maximum second derivative and level of noise. That's what we've done. So, what we achieved in the end of the 20th century, we've achieved the following. We was shown that we are able to attend the outputs with relative degree 2. And for such kind of systems, it is each mechanical system updated. We never need a sliding loop surface. This means that in this part, the linear reproduction was done. Why? Because we show that we are free to follow the guide, and we can guarantee that you will be happy before you will die. But it was not complete, because if you would like to adjust the chapter, it was necessary to do continuous control when the relative degree is 1. The chattering attenuation for relative degree 1 is down, but not more. So what was still missing? First of all, output with arbitrary relative degree was not done, so it was impossible to guarantee that if you have relative degree more than 2, it is impossible. The new religion was not ensured. Second, it was necessary to attenuate the chattering for outputs with arbitrary relative degree. So, and moreover, this promoted exact, theoretically exact differentiator providing the best possible accuracy, but the differentiator of arbitrary order was still absent because applying one step-by-step supercritical degree differentiator, you cannot achieve best possible accuracy. So, you see, in the early 21st century, it provided arbitrary laws. It looks like the following. First of all, it is first order sliding law. Here, I need to tell you something. So, it looks like sliding law which allows me to follow the parabola. And this is not parabola with 1 by 2, and it allows me to reach sigma and sigma naught in finite time. Unfortunately, I have Q infinite here. So I'm not sure that I will follow it. And the behavior will be like a twisting behavior with Zenon phenomenon inside, but finally we will reach 0 in 5. Then you can see this is a third order sliding. What do you see here? You can see here precisely, first of all, my wish to follow this surface. Then my wish to follow this parameter. It will be not that. Why? Because I will go to the surface and make a twisting behavior, but reach finally to parabola and also with twisting behavior go to zero. That's how it works. So, what we've done finally. Also, of course, we derive in the same way differentiators, and they do give a possibility to realize maximum possible precision for such a class system. What's happened here? This is precisely the last stage of the art made by graph. Okay, I need, first of all, universal controller which allows me to adjust the shuttering and which allows me to follow to the track, to track something for the black or gray box. What I need to know about the system, just one stuff. I need to know the structure. I need to know, for example, if it is a robot, how many degrees of freedom we have, and how many degrees of under-activation we have. So, and you see, so if we know that relative degree is not more than r, and our policy is lazy, and they told me I can deal only with very smooth control, moreover, kinda 2 times smooth. What I'll do? I'll take the output, I will take differentiator, and then I'll try to put it and to take number of the derivatives required to realize R plus T sliding. So then key order will be eaten by policies, by actuators. And the plan will need also relatively R, so I'm done. In which sense I'm done? I never asked you to go no. So I never asked you about diet. What I'm asking you is just output, input, and the structure, but let's see, not precisely. I need just how many degrees of freedom you have. After that, I'm sure that you will be happy and you will be. That's all. Now, some videos will
differentiating this. So this is the break that takes care of the noise that is going on because the quantum is linear on the number.
no point.
So there's also the positions, there's
looking for that, let's say. Anyway, you are putting, you put what? You put all the states to make the point. Yes. So if you have doubt, how you can find to the presence of saturation or without any movement in the plank, how you can find the state? You need differentiate. So you have to choose a differentiator which gives it is observed. What is differentiator? It is observed. You need to make a differentiator which allows you to have a minimum possible noise. No! I've shown you that I can deal without filtration. That's it. Moreover, what I have to ensure is, you see, you asked me about those. Yes. What you need to do. So, the second video story, you know that it is difficult to find in Mexico a small bottle of tequila. That is why it is done with single light. You see, the experiment here, the same water, the same pendulum, 25 grams. So, and Professor Preston asked me about the name of structure. To show that it is good, I put it here 5 grams without adjusting the control. And it is still robust for signal. So, it is not the main of the structure.
no, what is this game?
So you've seen the video before.
No,
Before, when I
yeah.
videoed it as well, let's say it will be the next step. No, it's possible. It depends on the motor. But if you will draw the motor, so thank you for suggesting. Okay, so continuing your answer to your question, you cannot ask the water to be muted. You can ask the best possible interpretation. What I've told with respect to the noise, that it will be best possible realization. We've made very careful comparison with copies published in last CDC. We've made 2 papers comparing our differentiators with the so-called high gain differentiator made by Halil. Halil took our challenge, and he optimized high gain differentiators in order to be competitive with us. And he thought, if I will optimize my differentiator, it will look like yours. I just one problem. He needs more information. So he needs the information about the noise, how strong is the noise. We don't need it. Our differentiator automatically will give you a maximum possible precision without knowledge of the noise. But if we will use this precision, we can make it even better. We can make it even better. So, of course, the provider will give you the data, so the sensor is last. But you are never sure if they are less or more than those noise. And also, in the time, they can be changed, like it's happening in your car. So it will be simply more old, and it will lose its parameters. But that is why you need every time, if you are using high gain, you need a chat. Now this machine will do it first. Okay. So, do I have a little bit of time or not? 10 minutes. Perfect. So I just would like to tell a couple of words more about Finland. We just published a textbook, which is a first textbook about new generations of sliding mouse control. It contains also the set of problems to solve. And for our friends, it's also the book of solution. Because there is this another book, 200 pages of solutions, exercises which are inside, and so it could be used by professors by special request, at least in the year. So, then, of course, I'd like to introduce the main lines of research which are giving and we are providing in my lab, which is called sliding control lab. So, normally we are dealing in 6 general directions. First of all is design of algorithms. Second is analysis of algorithms. That's what we'll tell them that this is a part of policy. Then we are still working on surface design. That's the part of the church. Then we are working on observers, because observers are building of our sliding computers, and we need first of all to grow the classes of the system for which we can multiply such observers, and from the other we also investigate the properties of the differentiators we are using. And then, of course, we are dealing with compensation of unmatched uncertainty, because as I told you, matched uncertainties will be treated by sliding surface, by sliding control, very simple. But the problem of treatment for unmatched uncertainty is the problem. And then applications. In applications, we can write at least 6 more boxes, but first of all, let's go step by step. First of all, we are developing language-based approach to designing sliding surfaces. So we are doing it together with Professor Heinemar, which is professor of Institute of Engineering of Milan. And the main results here are the following. First of all, Professor Marana is absorbent designed Nonlinear function, which is not only most used. It doesn't have a deep meaning, but it still can apply to analysis of supercrystalline light algorithm, and we can estimate the convergence time, and we can use a standard Lagrange-based technique, and a Lagrange equation-based technique, or LMI technique, to find the conditions of convergence for supercrystalline light. The second result that I'd like to mention here is precisely the paper transactions, which we've shown design a very convenient supertwisting. So the video you've seen how the system, the controller is adapted to the application, the last two, is based on such kind of control. Then, Tomato Sanchez will present the set of the papers, the CDC-12, CDC-2, for level of function based on different site algorithms connected with site function, and it is also very important for. Then, what we are doing together, I have a common project of collaboration with the Indian Institute of Technology, and in the framework of this project, we developed new classes algorithm. This is supertwisting like algorithm, but for arbitrary order systems. And we designed a Lyapunov functions with these Lyapunov functions because they are different in each stage. And we are planning to publish this soon. But that's very important and still open question because the number of derivatives you need to save in order not to differentiate too much. That's the supertwisting based algorithm. Then we are developing with you see these two guys are French. One is Denis Yefimov, another one is Andrei Polyakov. They are working in reality. So, and we are working with them with so-called implicit Lyapunov function based approach. Why it is important? Let's see. What is the traditional way to test an process? You are designing controller, maybe God will help you, and then we will ask the God to help you to prove the stability of its properties, which is really difficult. So, what was a new idea here? The new idea behind this approach is very simple. You are designing Lyapunov function and control algorithm simultaneously. When you are doing it, you don't need to ask the God twice, just once. That's the point. So, because if you are designing the control algorithm based on this approach, you have controller automatically, and the proof of stability also. Then, that's the new stuff we are dealing with. That's very important. Why? Because with my student, we've developed so-called fixed time controllers and observers. I'll explain you the situation on the example of humanoid-based controller. Let's say you need that no control will work correctly. So you will not have a model, or you will have very nonlinear one. For a very nonlinear model, you need to prove separation principles. That's Professor Bretzman asked me about separation principle. So if the system is nonlinear, it's a good job. So what you can do, you can ensure that your observer or your differentiator will converge in fixed time, and then you can switch on controller because you are basing in the correct information. So you need such an algorithm which will converge in fixed time, so before some given time. So you can not only be happy when you will be alive, you will be happy to 40 years. That's the point. So let's see. This is precisely the time of convergence for level differentiation plus one based on supertwisting algorithm. So I'm drawing initial conditions in orders. If it is around 10, this is the time of convergence. You see, each order of the error of initial condition, the time of convergence is finite but growing. So what we found asymptotically. The asymptotic, in which we are sure that the differentiator will converge before. That's precisely such style of differentiator, you see. This is a normal differentiator with a half. So half will give you finite convergence. But this is a new term which you never seen before. That's a term which was afraid Professor Belsman, because normally if it is with the incorrect side, you will go to infinity and finite time, isn't it? But if we will put it in correct side, Hume gives us the finite time to escape from infinity, because it's in some sense conversable, let's say, reversal. And it was published for the first order differentiator in number 9 of automatic catalyst. Here it was published for arbitrary order differentiator. So then another approach. We are trying to develop adaptive constraints. Why? Because you see the same model can give you a good problem, but you need to use a less energy. So adaptation of slightly more controller results in the better chattering adjustment, and moreover, what does it mean? You need much less energy. It doesn't depend on the order of controller, because you never can kill chattering for 100%. You can just make this frequency lower, but it will still oscillate. That's short, that's for sure. The problem is that the frequency and the magnitude of oscillation will be less and less, but you will still use an energy. So what we need to minimize an energy consumption and stuff like that. So we've done 2 good papers with that. One is published in Transactions number 8, and another one is under consideration in International Control Properties for Nonlinear Control. There are 2 students working in the process. Unfortunately, Felix Gonzalez has now in his private company sources. Maybe he'll use our controller. So here, we are coming to the part of the matter. We are working here with Professor Schwartz. Why it's very difficult to say like because people from practice, people from math, they are asking about phase and gain margins controllers. But sliding controllers in his behavior, they are completely nonlinear. So that is why it was necessary to elaborate special tools how to convert it with linear. That's what we are doing with Professor Stessel from Alabama and with my student Antonio Rosales. I think that the results are very important if reported in CDC, ACC, and there is one journal publication will be published soon. So we explain how we can consider sliding controllers because it's very new connected to chattering. So we need to use there the level of tolerance of the system in order to explain how we can measure the margin, phase margin, and gain margin for such kind of controllers. Another way to see to adjust the chattering because it's every time, what we need to make it compensators. And we made this type of compensators to deal with Professor Koiko. What we are doing. The problem is that what's happened with the chatting? We need to see it in nonlinear way. So we need to use this describing function for more advanced methods to find the frequency and amplitude of oscillation into the system, and then to adjust, like we are every time using some compensator for example, some compensator for linear part for matrix form, and then you can see, for example, this is precisely the graph which shows the initial intersection, so the initial level of magnitude and frequency of oscillation for a standard situation between, say, master for original form, and then compensate quantum symbol. Then, next stage. What we are doing for sliding surface. We are not absolute theorists, we are not using every maximum order sliding surface. We are not using maximum order sliding because it's not every time necessary. What we have to do, we can make a combination between order of sliding control and order of reduced dynamics, and make for the dynamics different sliding surfaces. This is an example reported in the paper by David Hernandez and Fernando Castañez. She is our PhD student, Fernando Castañez from Simulesta, and we propose their generation of Ackermann formula, how to use an arbitrary sliding order sliding mode and how to design for that sliding surface. Another approach is how to optimize the sliding surface through the group, and it is the second stage of consideration of quantum transaction. This paper is my PhD student, is my estimate. And the third is precisely what we are doing now. Why? Because it is how we can combine agent field and integral sliding control of arbitrary order in order to minimize the influence of much perturbation on the system, which is just partially controlled by how you can use it. You can have much perturbation, you can minimize the influence, you can compensate completely that much perturbation and make and adjust the influence of much perturbation. The first result will be reported in CBC field. Currently in CBC field in December, and I hope it's also for the journal. I suppose that the most successful area we are dealing with is observation thought, and we've made, based on higher order sliding observer, we've made a lot of results. Around 40 journal papers, and this is my PhDs, former PhDs, these three guys. They are making very, very good results, and all of them, they have at least publications in both transactions and Automatica. And moreover, they have now, all of their free, they have in this, more or less in this direction, the publications themselves without me about the area. So the main idea here is to match together the classical observation method with the higher order sliding shape. So we are dealing with nonlinear full detection and stuff like that. So this is the main results. So strong observable linear system, strong detectable linear system, nonlinear with defined relative degree, strong observability for nonlinear system. And now, one of the main issues how to combine uniform convergent differentiators with all this stuff. And we are working on that, applying it to different hybrids. I'll tell you later about that. And then it is a large perturbation free. My group will operate with at least 4 approaches to do this. First one is direct differentiator, growing relative, direct differentiation, growing the relative degree, and it is published in Transactions on Calculate Project 2011. So that's more or less interesting stuff, how to put together backstating and sliding moves. So what's the problem? The problem is that if you have a much perturbation and you have system in Rumovsky or strictly feedback form, so what you can have x1 dot equal to x2, x2 dot x3, so in the last line you have all of this stuff. But imagine that you have perturbation in the first line. What's happening? You need to compensate something you cannot have an access, because the access is to the last derivative. So what you are doing? You are doing the following. You would like to have sine function in the first equation, but it is impossible because you need to differentiate it in the last line. What we suggested? We suggested to put corresponding level of Nonlinear control. In order to make x2 smooth and compensate the perturbation in x1. And then you will differentiate it, but you will have finally the corresponding order of sliding control. So you can do what classical backstepping cannot. Why? Because you have a much perturbation, which can be constant, which can be developed, which can depend only on time, and you can not compensate it with backstepping, but with this combination you can compensate. So you can see our paper is now automatic transaction. One is to be published. So, and here is another approach. What we are doing here, the following. First of all, we have very good observers which can not only observe and estimate the state, but also the perturbation. So what we are doing now, we are estimating the perturbation, and then we are compensating in different ways. If they are matched, no problem, you can compensate it directly. If they are matched, you can compensate it through surfaces because you know the perturbation. That's the last paper published in International Journal of Law, and another paper in our matching to the published. That's precisely what the work of Dr. Alejandra Ferreira, which you are very good to see because she proved as a postdoc student in this. So, this is the same stuff about hybrid system. Sorry, Luis, I will never finish. Better stop here, see that. Okay, I will also mention very important for me at least, a work by Dr. Anna Galiano, which makes not only theoretical study of practical relative degree and how it can be used for a medical problem, it also implemented it in experimental. Why? So it constructed a special stuff in which mouse can walk, so making exercises. Which it was put to draw, let's say, good to mouse. And injection of glucose, she was very ill with diabetes. And then the diabetes will treated by the glucose, and it was a good experimental result. You know, to promote a field patient, it's very difficult because you need 1,000 permissions and at least 10 years to promote the. So he also was, let's say, tested the idea of practical relativism. It means dealing with medical problems, you never know the truth, because when you care to the next doctor dealing with such disease, he'll tell you, okay, this parameter is very important. Then you will Google his daughter, and you will see that this parameter was precisely his clinical. So he'll never allow you to make put it off from normal. So, and we've seen at least 25 models of the injection, and we've understood that it is impossible to deal only with doctors. We've started very simple stuff. We've understood, what we need to make a slide model. We need to know the structure. So it was impossible to compare the parameters of models because even doctors cannot reduce or express one parameter through the other. So we need to make a job ourselves. So we took the simplest model and we started to simulate the reaction of the patient on simple injection. And then it turns very interesting stuff. That even if we see the models for the 3 or more than 25, so the simple controller operated for the third order was working more or less good, even there are 25 relative to 25 dimensional model. So, and then we put it to work in the experiment, prove some theorems about singular population, and then it was working. So, in short words, so if you'd like to be married, never use 25 parameters for that. You need to be reasonable enough if you would like to make a decision and make a control. Because with 25 parameters, you will never make it. That's maybe my conclusion, because of course, you see, there are a lot of different applications. They are working on the crane systems. If you want, I will show you how it goes there. We are working, and I made a book about estimation of parameters of the car, but you can find it on my website. Just Google Friedman, that's all. Thank you.